All right, so November 10th, those of you in class, ignore me. Just starting a video. We're starting with this, just giving students time in class to work through this circuit. If you look at yesterday's video, trying to take the circuit to the logic expression, or not to the expression, sorry, to the truth table. You put test points after every gate, and it can be helpful to compare if you do it in the same order. So after the inverter, make that 1. After this AND gate, the 2, the 3. You don't need one here because that's the output. And then this path, start back near the inputs, 4, 5. Again, don't need one here. So we had test points 1, 2, 3, 4, 5. And then I'll do 1 just to get us started. And if you in class here want to, if you're kind of stuck, struggling, I'm going to just pick a random one, literally at random. You're going to want to use a pencil, and you're going to want to write lightly, and you're going to want to erase all these zeros and ones that you put down. But what we're going to do is we're going to test 0, 1, 1 through these logic gates, and we're going to think about what would 0, 1, 1 translate into. So I'm picking one at random, so I don't always start with 0, 0, 0. So you would take, each one and follow its line and kind of, see what it turns into. So 0 here through an inverter becomes a 1. Then you get to an AND gate, which you need the other input. So we'll come back. That's a 0. Okay, so there's a 0 there. This is a 0 down to here. All right, this AND gate at test, kind of right after test point 1, a 1 and a 0 with an AND. You got to have both ones to get a 1. So that's going to be a 0 at test point 2. So we can start filling this in too. So test point 1 was going to be a 1. Test point 2 is a 0. All right, I need the input here. So that's a 1. 0 and 1 with an AND is a 0. So test point 3 is 0. All right, I did? I'm not. This 0? Oh, it's supposed to, thank you. Because I said I'm doing 0, 1, 1. Thank you. Okay. So, oh yeah. Thankfully, I got pencil here. So, that's definitely going to change it. Okay, so that's a 1. So, thank you. I'm testing 0, 1, 1. So I need 0, 1, 1. I didn't even see my own mistake. So now 1 and 1 and is a 1. So now my test point 2 is a 1. I love to model that we all make mistakes. That's all I'm doing. So don't feel bad if you make mistakes. So 1 here, 1 and 1, that's a 1. All right, and then honestly, I know the output now because that's an OR. So as long as I have at least 1, 1 on an OR gate, I'll get a 1. But I still want to fill out these last two. So on C, I've got a 1 here going through an inverter becomes a 0. And then this other AND gate, that is coming from B, so that's a 1. So I have 1 and 0 with an AND is going to be a 0. So test point 4 is a 0, and test point 5 is a 0. But that's what you're doing. You're going through the whole thing. And then, when you're finally done, you're going to find all the ones, which we'll do that in a second. And then we'll write out the midterm expressions, sum of products. So I found 3 ones, and they were here, here, and here. And I will just point this one thing out. With test point 3 and test point 5 being the two that feed into an OR gate, if either of those were a 1, then with an OR, as long as I have at least 1, 1, I should have gotten an output of 1. And if they were both 1s, then I should have had an output of 1. So if I record, what did I have here? I had 1, 1, 0, 1, 1. And then on this one, I had 0, 0, 0, 1, 1. You can see I have test point 5 as a 1, so that should have given me an output of 1. Up here, I have test point 5 also a 1, but not both. So 3. So anyway. All right, so once we found those ones, we're going to write the Minturn expressions, right, capturing this combination of inputs of A, B, and C, and then we'll write our sum of product expression. So this one is not A, B, C, which looks like, right, not A is the A with the line over top, B is no line over top, and then not C, put the line over top. So, right, this one's going to be not A, B, and C, and this is A, B, and not C. And then the sum of product expressions, we're trying to say that any of these combinations gives me the output at F2. So we say F2 is equal to these expressions with a plus sign in between, and we will read that with the word or. So not A, B, C, or not A, B, C, or A, B, not C. So, is it hard? No. Is it tedious? Yes. It's time consuming, yeah. And easy to make a little mistake, as I demonstrated. Very intentionally planned to make a mistake. All right. So here's the next one. This one's way better. We're going to go from the circuit to the expression first. And here's all we're going to do. It's way easier. We're going to track X, Y, Z as the values, X or not X. So if we start with X, I'm going to get to an inverter, and it's going to become not X. Okay? And then Y is here, so I'm going to track this wire here, is Y to the AND gate. So when I get an AND gate is combining, it's creating the combination of the two inputs. So the AND gate creates this combination of not X and Y. And so with AND, it's a product. We put them together like that. And then, let's see, the next AND gate, so this is, I'm just going to write it even closer. I don't really need to write it again, but write the same way. This AND gate is going to combine not X, Y, and Z. And so coming out of this gate, I get not X and Y and Z as a combination. And let's come back here. This wire Y is going to hit the inverter. So coming out of the inverter is going to be not Y. The other input to this AND gate was X. So coming out of this AND gate is going to be X and not Y. I'm going to keep my inputs always in kind of the same order. Usually it's alphabetical, but if not alphabetical, at least kind of keep them in the same order. So even though I have Y on top, I'll still, multiplication's commutative. I can not Y, X is the same combination, but just for reader friendly and for ease, I think keeping that order the same will be very helpful. So coming into this OR gate, I have X not Y, or not X, Y, Z. So my sum of products, OR, is where we use a plus. So it's going to be not X, Y, Z, or X not Y. And that's F1. That is way easier, is it not? Now I get to take this and figure out where do I put the ones in the truth table. Well, I have two combinations listed. The first one is not X, Y, Z. That one's very explicit. I know that to be 0, 1, 1. So I'm going to find 0, 1, 1 right here and put a 1 there. So that's not X, Y, Z. Is that okay? The next one, however, though, doesn't specify Z, right? That means it's I don't care what Z is. So in terms of putting this into binary, I'm going to say X is 1, Y is 0, and then I'm going to put like a kind of an X here for binary. I'm going to say don't care. I don't care what that is. So I'm looking for 1, 0, right? That really means 1, 0, 1 or 1, 0, 0. Both of those are good because I don't care what those are. So it can be either or. So if I can find a 1, 0, which they happen to be side by side, both of those are good. They're both 1s. So this is X not Y, and this is also X not Y. All right. How about you guys try one of those on your own? This one will be way faster. All right, so we're going to trace through this example, and if you didn't do it yet, or finish it, maybe you can kind of still beat me. So if I trace through, I've got A becomes not A. This is B, branches here and here. So this AND gate becomes not A and B. Let's see, this line is C, goes to those two places. So I've got C becomes not C. This AND gate is going to give me B and not C. This AND gate is going to give me not A, B, C. All right, and then the OR gate at the end is going to combine this with a sum. So not A, B, C, or I'll just write it again here, B, not C. All right, so that's basically our answer, that F2 equals not A, B, C, or B, not C. All right, so then converting that into the truth table, this one is 0, 1, 1. That's easy, right? And this is a don't care what A is, 1, 0. So 0, 1, 1 is right here. And then don't care, 1, 0. So I'm looking for just a 1, 0 in the second two columns, and I got it here and here. So then I fill in the rest with zeros, and I got it. And go back. Let's see, is that? I don't know if you guys, I'm pretty sure it's the same example, right? If this looks familiar, but if we go back to the other one where we did the table first and compare them, these are the exact same. Get the inverter to the AND gate, right? If you kind of trace those, it looks identical. So we should have the same truth tables, which I didn't fill in all my zeros here, but it was the same, right? 0, 0, 1, 1, 0, 0, 1, 0. Same thing. You can't see what? You can't see my screen. Well, the people at home can. The people at home can see better than the people in class because I didn't share my screen with them. All right. Anyway, lo siento. Well, now you can check your answer because really I was trying to, that was a you try anyway. So let you make sure that looks right. So you can pause it at home, but check here. I just wanted you to see the other one we did. They were the same circuit. So we actually should have had the same truth tables, which we did. Now the expressions look a little different, which we're still going to get to later. That kind of gets planted, but pause where we're at. All right, so this is the activity that follows it, which I'm going to have you guys work through. You are going to, you've got a little one to trace, right, kind of the zeros and ones through. Thankfully, there's only 2 inputs, so you only have 4 to check. You got 4 test points. So you're doing the truth table first, and then you're going to find the minterms and write out the sum of products. Reanalyze a simple circuit using the technique where you first extract the logic expression. You're going to get the right trace X and Y through instead of zeros and ones and get the expression. Okay, and then you can use the expression to fill out the truth table. Now, this circuit and this circuit are the same, so we're kind of taking both approaches and then comparing and contrasting, right? How does the logic expression and truth tables obtained from the 2 techniques compare? Are they the same? Should they be? Etc. I think you probably already kind of think you know the answer to that. They're going to repeat that with a slightly more complicated circuit. So, right, let's analyze one that's more complex. And again, this is setting up, if we do it, I know it's tedious, but this may be one of the last ones we do like this, right here. So there are 3 inputs, so you got 8 of these to try. I'm okay with you guys not writing out TP1, TP2, TP3, but you guys see how easy it is to forget to erase a 0, and then you see the 0 and you kind of track it. Like, you just got to be careful. The main goal is to get the correct ones at the end here, at the output, right? So erase well, be careful, take your time, but think through it and see if you can get the correct ones. Do you want me to give you the hint of how many ones I got? I had 4, right? I'll give you the hint that when you do this, out of the 8 combinations, 4 of them are 1s. So half of them are 1s and the other half are 0s. You could always choose to do the easier one first, the easier method. And if you take your time and do it with where you've got the expression, maybe that helps you feel like you're doing this right or wrong. But do trace the 0s and 1s through, okay? And then we want to compare. We want to write the expressions based on the techniques. If you do that, we'll have something tangible and real to look at and compare and contrast. If you just do one and then kind of copy the answer into the other, you're not going to have the same ability. So that's going to be your next to-do. Good little things to observe or discuss once we get down to that, and there's some questions to follow up. So